first. First, what is DNA extraction? DNA extraction also means DNA isolation. It's a process of purification of DNA from sample using a combination of physical and chemical methods. That means we just want to get the DNA or harvest DNA, use some physical or some chemical method. And this DNA should be purified. We do not need the contaminated protein or other things, just the DNA. This is the DNA extraction. And why we want to get DNA? Why we want to harvest DNA? The purpose of DNA extraction is if we get the purified DNA, we can do some further investigation, such as PCR, and we will do the PCR today. And we can also do sequencing and other investigations. And because our genetics is just microgenetics, so DNA extracted can from anything such as plants, bacteria, virus, and animals. And the medical DNA, we extract the DNA from human cells. So the DNA extracted from human cells, we can use it to do lots of disease diagnosis, such as genetic testing. For example, if a newborn baby which has some syndrome, we just guess it related to one genetic disease. Then we can extract DNA from this baby and to do the following investigation and to diagnose the disease. And another, we can investigate the genes involved in disease, such as Parkinson's disease, such as cancer. For example, if in one family the dad and the son have a disease with the same syndrome, so maybe we can think if there are some relationship with genetics, then we just want to extract the DNA from the dad and the son and sequence or do other investigate and to measure some disease if there are some same disease, same genes, mutation or other changes in the disease. And this can also analyze for forensic evidence. Even we can extract DNA from the hair, from some very things belong to the crime. And this is extraction of DNA used for. And there are lots of methods to extract DNA. However, most DNA extraction protocols consist of two parts. First, we need to break the cells, and then we get the DNA out. So, a technique for first pass is a technique to slice the cell gently and soluble the DNA. This is the first step we need to do. And another is enzymatic or chemical method to remove contaminating proteins, RNA, or micromolecules. So that means first we just collect cells, then force the cells open to release DNA and separate DNA from protein and debris and isolate concentrated DNA. Then we can use this DNA. This DNA is purified and we can use it to do lots of experiments. And there are lots of kits for DNA extracted. And we just select one kit. This kit, the principle of this kit, this genomic DNA extraction kit, have this principle that in the high salt state, DNA purification resin absorbed DNA specifically, while in a state of low salt or aqueous solution, DNA was eluted down. That means in the high salt, the cell break and there are something resin. This resin just absorb the DNA, not the RNA or not the proteins, just the RNA. And after this, we harvest the resin. The resin, we absorb the DNA, we harvest this and discard all other things, the debris, the proteins, all other things we just discard. And then we put the resin in a state of low salt or aqueous solution. Then the DNA will separate from the resin. We can collect the DNA for the further investigation. This is a principle of the genomic DNA extraction kit. And I just said there are lots of kits for DNA extract. So the different kits have different principles. This principle just based on the kit we used today. This is the kit we will use today. And the reagents we use today is first the purification resin and GM binding buffer and washing buffer, purification column, ethanol. And this is a protocol, and I will tell you the detail. First, discard the culture medium, wash cell with PBS once. Today we just harvest or extract DNA from the culture cell. Actually, sometimes when we diagnose a disease, we just use the cell from the blood. However, it's difficult for we do in the class, so we just use the culture cell. And the protocol is the similar. So first you will get a flask which has still the HeLa cells on the bottom, and just discard the culture medium, discard it, and add the PBS into the flask and gently shake it, and then discard the PBS. After this step, we add 0.8 microliter PBS into the flask. This time, do not discard the PBS, just keep it in the flask. Then we will use a cell scraper. This is a cell scraper, and we use this just detach the cell. Can you understand that? We detach the cell. After this, we transfer all the cell suspension into a 2 ml tube. This is a 2 milliliter tube. And this is round, the bottom is round. This is 2 ml tube. And we just transfer all the cell suspension into this. And then add 1 ml purification resin. I will give you this one, purification resin in the tube. And in water, tube 5 to 6 times. Gently, just like this. You can do like this in water. Yeah, great. And then leave this to incubate for 3 minutes, just at room temperature. And during the 3 minutes, you wash the tube once. Can you understand? When you incubate this at room temperature, you wash it once. And then the next step is spin at 5,000 RPM for 10 seconds. It's very short. And discard the supernatant. Understand? Then just discard the supernatant. Because today we will have what step to spin the cell. Then we suspend the pellet in 1 ml gene binding buffer. I will give you the gene binding buffer and still invert the tube. Then spin at 5,000 RPM for 10 seconds again, then discard the supernatant. And follow the resuspend the tablet in 0.5 ml of washing buffer, another buffer, and invert the tube again, and then spin again. Spin at 5,000 RPM for 10 seconds. Still discard the supernatant. Repeat this step again. That means we will add another additional 0.5 ml of washing buffer into the tablet, and then invert the tube and spin at 5,000 RPM for 10 seconds. Repeat this again. And then you can see the pellet, the color of the pellet. If the pellet is white, should be white to cream. You can see if it's white, it's okay, you can do next step. However, if you see the pellet is still yellow, you should repeat the washing step again. Sometimes because sometimes when we use the blood, this will need. Sometimes you will see the pellet is still yellow. However, when we use a culture cell, always it will be white. So we just need to wash 2 times. It's okay. Then the next step is add 0.8 ml of ethanol to pellet and resuspend the pellet. And here we do not need spin again. We just transfer all the things. That means the DNA and the ethanol transfer all these things into a new purification column. This is a purification column. You can see this is the one side. This is a purification column. And transfer all the things into the purification column. In the upper one, because this is true, just the upper one, transfer all the things into this. And then spin at 12,000 RPM for 1 minute. Then we will see the ethanol will go through the column, go through this into from the upper one to the lower cell. Then we discard the ethanol in the lower collection. Just discard. You can like this. Just discard the ethanol. Understand here? Okay. And then spin again. When we do this step, we do not need add anything. We just spin it at 5,000 RPM for 1 minute. Then we will see there are still some ethanol from the upper to the lower. Then we just discard the ethanol completely. Then this will done, and we will go into next step. Then we just put the purification column. Just discard the lower one and put this into a new 1.5 ml tube. This is another tube. It's a clean one. You just put the color into this one. You understand here? And then we will add 50 microliter water. This water is ultra pure water to the rising of the purification column. That means we will add the water directly in the middle of the column. You understand here? Okay. And then incubate for 3 minutes at room temperature. After this, we will spin again at 5,000 RPM for 2 minutes. Then we will see there are something in the 1.5 mile tubes in the upper one. This is our DNA. Then we can discuss the color. We just want the DNA is here. Everyone clear here? Everyone understand here? Okay. Then the genomic DNA is in the tube, and we will do the next experiment. The next experiment is PCR, and we will use our collect the DNA. PCR is polymerase chain reaction. This is a technique to just mimic the natural DNA replication. We know there are DNA replication in our human body, so the PCR just mimic the natural DNA replication. This is in the laboratory. This is not this is in vitro. And this is a technique to amplify a single or a few copies of a piece of DNA across several orders of magnitude, generating thousands to millions of copies of a particular DNA sequence. That means this is a DNA. This is a DNA, and here is a part of DNA what we want. Then we can use a PCR technique. Then we can get lots and lots of the purple part. And here, this is a PCR. We just replicate the DNA in the laboratory. And this is the DNA application technique. And a basic PCR setup requires several reagents. First, the template DNA primers, nucleotide, DNA polymerase, and buffer. I will tell you in detail. First is the template DNA. Template DNA means it contains the sequence of DNA you wanted to amplify. I just show you that if this is a DNA, you can amplify the whole sequence if you want. You can just get a part of the DNA. That means you can select which part you want, and this we call this template DNA. And this DNA can be from animals, plants, viruses, and bacteria. However, for our medical genetics, always from human beings. And today, the template DNA is just the genomic DNA extracted from the culture cells. You will do the genomic DNA extraction first, then you will do the PCR. This is the template DNA. And another is the primers. If we just have the template DNA, we cannot replicate this. So we still want something, the primers. Primers is the small segments of a single strand DNA, usually about 20 nucleotides long. That is about 20, maybe is 18 or maybe 24, 25. That means it's very small, the primers. And the primers bind a specific region on either side of the target DNA sequence and init the replication of the target DNA at that point. That means if we want the purple one, then this is the primary one, and this is the primary 2. And between the primary 1 and the primary 2 is what we want. This is our template DNA, and this is a target sequence we want. This is about the primary, and another is the nucleotide. We know in the human body, if we replicate the DNA, we need something like DATP, DTTP, DCTP, DGTP. This is still need in our PCR. This is DNTP we will use, and all four nucleotide triphosphate, the DATP, DTTP, CG we will still want. And this is our one step in if this is A, G, E, C, and this is our primer. Then we will add the T here, C here, A here, and G here, and use this tag ATCG, and they will replicate the DNA. And this is the nucleotide which we will need in the PCR. And another important thing is the DNA polymerase. That means how do we put the G in here, and how do we put the A here? We will use an enzyme. This enzyme is DNA polymerase. The DNA polymerase is an enzyme that makes a new strand of DNA through the sequential addition of a nucleotide. And we always use the DNA polymerase in the PCR is type DNA polymerase. And this type DNA polymerase is from a bacterial, and this can work at a very high temperature. And that means at high temperature, the enzyme won't lose their function. They can still work. This is the DNA polymerase. And another is the buffer. The buffer providing a suitable chemical environment for optimal activity of stability of the DNA polymerase. So the buffer will provide alternate pH and some other things. So this is the buffer we must use. And there are some main steps of the PCR. The main step have 3 steps. The first is the signature DNA. We can see here is a DNA oil at 95 centigrade, or at 94 centigrade. That means above 90 centigrade, the DNA is denatured. That means the 2 strands are separated, just like this. This is our template DNA, and this is our target DNA, and this is the denatured DNA, the 2 strands separated. And another step is anneal, primaries anneal, and 40 to 65 centigrade. The primer with anneal, their complementary sequence on the single strands of the DNA. So that means our primary can bind to our template DNA. So we can see here, if this primer can bind to our target DNA, that means the sequence of the primer is what we want. It should be complementary sequence to the strand of DNA. Understand here, this is step 2 annealing. And another is extension. That means DNA polymerase extend the DNA chain at 72 centigrade. DNA polymerase extend the DNA chain by adding nucleotides to the 3 ends of the primaries. We can see the purple one follows the primary is the arranging one. This is the extension, and this is another, the third step of the PCR. This is the whole steps. Here we can see together. First is the denaturation, 1 minute and 94 or 95 centigrade. And then the two strands separated. And another is annealing. The primary can bind to our target DNA. This temperature is lower than the temperature we need denature. It's maybe 40 to 65 centigrade. And another is extension. We can see these are colorful things. These colorful things is our DNTP. It includes DATP, DTTP, DCTP, and EJTP. Then the target DNA polymerase will extend the primaries. We can see this is our target DNA extension. And so we can see the basis of DNA is the temperature changes from the about 90, then to the 54, and then to the 72. And based on the temperature changes, the effect that these changes have on the DNA will separate it, and the primary will bind to the DNA and it will extend it. So this is the core step of the PCR. And this we can see here is the which extension. This is the nature, the two strands separated, and the primer bind to our DNA and extend with under the DNA polymerase. In a PCR reaction, the following series of steps will repeat 20 to 40 times, just like this. 1, 2, 3, 4, then 20 to 40 times. We call this cycles. And then if we have only one copy of the DNA, just like the original template strand is a blue one, and after one cycle, after 2, after 3, and after 4, if all the deletions is optimal, we will have lots and lots of targeted DNA we want. Here is the code about the PCR. And today's experiment we will do is the genomic DNA is from the culture cell, and this is our template DNA. And we will use a tag PCR master mix. In this mix, will include the tag polymerase, the DNTP, and the buffer. So we just need to add once. We just need to add the mix in our tube. We do not need to add the tag polymerase and the DNTP and the buffer. We just add once. And the primary we use today is APGGCAAGCCAA. This is primary one, and this is our primary 2. And sometimes the two primary is the same long. However, here we use the different. The primary 2 is longer than primary 1. It doesn't matter. If we can get the target DNA that we want, it's okay. This is the primary we use, and the water we used is ultra pure water, and the template DNA I just decided. And we add all the things together. Here is the PCR tube. PCR tube is different from our tube. I just show you because it is very small. This is the PCR tube because we should put this into the PCR machine. And we will add first the ultra pure water, 10 microliter, and primary one, 0.75 microliter, and the primary two, 0.75 microliter, and the template DME 1 microliter, and the tech PCR master mix, because it's 2 times, so we will add 12.5 microliter, and the total volume is 25. This is, we add all the things into our PCR tube. Then we will put the PCR tube into the PCR machine. And the temporary protocol we use today is the first initial denaturing. First is 94 centigrade for 5 minutes. Then denature is 94 centigrade for 30 seconds, and annealing 56 centigrade for 30 seconds. And extension we used is 72 centigrade for 50 seconds. And this denaturation annealing extension we will repeat 30 cycles. We will repeat 30 times, and we call this 30 cycles. And the final extension is 72 centigrade for 6 minutes. And then we will hold the product of our PCR at 4 centigrade. That means after the PCR product will be stored in the refrigerator, and we will use this PCR product for further examination next week. So it's a good news for you. So you do not need handing the lab report next week. We will, you can write together the third and the fourth experiment together, because we will use the PCR product next week. And after you add all the things into the PCR tube, it's done. And I will put it into the PCR machine, and the PCR machine will do this by itself. And first, so we just wait for it done. So this is today's experiment. And first we will extract the DNA from the culture cell. Here we will do the first experiment. Okay.